In this video, I'm going to show you how to find the critical points of a function and then use the first derivative test to determine whether a function is increasing or decreasing, and to classify local extrema, which would be either a local minimum or a local maximum. So here we're given a revenue function and accompanying cost function where we're restricting x, the number of units produced and then sold, to the interval from 0 to 80. So we're only going to see where a function is increasing or decreasing, limited to that interval. So what we're going to look at is where the profit is increasing and decreasing, and find any local extrema that it has. So to get profit, of course, we have to take revenue minus cost. So if I subtract these functions, then what I get is, for my quadratic term, I have minus 0.2x squared minus 0.2x squared again. So my profit function would be minus 0.4x squared, and then I have plus 27x minus a minus 13x, which is a plus, so I have plus 40x, and then minus 430, so those are the fixed costs there. So now we have a profit function. Now we need the growth rate of profit, the derivative, for finding critical points and determining everything else that we need for this problem. So the derivative of this, we just use the power and sum rules. So I have power rule in this term, I have minus 0.4 times the derivative of x squared, which is 2x. So I have, sorry, recording got interrupted there. So as I was saying, I have minus 0.4 times the derivative of x squared, which is 2x. So I have minus 0.8x plus the derivative of 40x, which is just 40. And then minus 430 as a constant, so that doesn't contribute anything to a derivative. So that's our derivative. Next, we look at critical points. Critical points are where the derivative is equal to 0 or where it's undefined. In this case, this derivative is defined everywhere for all x, so we just need to see where it's equal to 0. So we need to see where minus 0.8x plus 40 is equal to 0. I'm going to take this term on the left and move it to the other side. So 40 is equal to 0.8x. So x is going to be 40 divided by 0.8. 0.8 is equal to 4/5. So dividing by 4/5 is the same as multiplying by 5/4. So we get 50. So 50 is our one and only critical point, x equals 50. Okay, now what we can do is divide the domain from 0 to 80 that we're given into two regions that are separated by the one critical point. So however many critical points you have, that will divide your real number line or your domain into that many regions plus 1. So on each of these regions, the profit function is either increasing or decreasing. So what we could do is choose any value between 0 and 50 exclusive and substitute it into this derivative. And if the result is positive, then it's increasing. If it's negative, it's decreasing. So I can plug in, for instance, x equals 1. So I have minus 0.8 plus 40, which is certainly going to be positive because 40 is a lot greater than 0.8. And if I substitute in a value that's greater than 50, for instance, let's say 60. So 60 times minus 0.8 is minus 48, plus 40 is minus 8, so the result is negative. So that means that the profit is increasing on the interval 0 to 50, and decreasing on the interval from 50 to 80. So increasing and decreasing. So at x equals 50, we might have a local extrema. So how can we tell if we have a local extremum, and if so, how can we tell if it is a local minimum or a local maximum. So for first derivative test, what it tells us is if f prime changes from minus to plus, so negative to positive, that's the same as changing from decreasing to increasing. So that means the function is decreasing at first, so decreasing at first and then increasing. So that would be a local minimum. Whereas if it changes from plus to minus, so positive to negative, that means the function is changing from, so if a derivative is changing from plus to minus, it means the function is changing from increasing to decreasing, like what is happening here. So a function is increasing at first, hits a peak, and then starts decreasing. So that is a local maximum. So that's how you can tell. Now, if it's neither of these, like for instance, negative to negative or positive to positive, then it's neither a local minimum nor a local maximum. So only when there's a sign change do you have a local extrema. So one sign change gives you a minimum. If you ever opposite, the sign change gives you a maximum. So in this case, we have a local maximum, and it's problems that require these in hogs, you specify them as an ordered pair. That would be the x value, so x equals 50, so our critical point, 50, is a local, is the x value for a local maximum, and then to get the corresponding y value, you would have to substitute x equals 50 into your profit function. So if I substitute x equals 50 in here, so I get minus 0.4 times 50 squared, which is 2,500. Okay. So then I have plus 40 times 50 minus 430. So that would give me minus 1,000 plus 2,000 minus 430, so that's going to be 570. So that would be the y value for my local extremum. So I have a local maximum at x equals 50, y equals 570, so profit equals 570. There is no local minimum because we did not get the right kind of sign change in the derivative. So once you have your function, take its derivative, see where it's equal to 0 or undefined. Those are your critical points. Use the critical points to divide your domain into regions on which a function is increasing or decreasing. Use the sign of a derivative to determine which it is, increasing or decreasing. And then depending on the sign change you get, when you get a sign change, that will tell you if you have a local minimum or a local maximum. So decreasing to increasing gives you a local minimum. Increasing to decreasing gives you a local maximum.